Okay, here we are at the last, I guess, bit of material in the course. All right, so we're going to talk about double integrals, and kind of makes sense, right? Because we've just got done talking about partial derivatives and for multivariate functions. So we're going to kind of do that process, take a look at it again with this idea of a double integral. And what I'm going to do is I'm going to actually show you how to compute some of them before I go over how to interpret what they represent. And I think after I do that, I think it might make sense to you. So, but essentially, what we're dealing with, if you remember, we started with a multivariate function and I took the partial with respect to y. I'm essentially treating x as a constant. So you can see that I integrated the y term here. Okay, or differentiated the y term here, okay? And same over here for this term, and I just tagged along the negative 3x squared. I just, took the 2 and multiplied it. That's where the negative 6 is coming from. Then, of course, which is 2 times 1 here. So if I was going in the opposite direction, right, the idea of integration is opposite of differentiation, right, the inverse operation. I'm going to take this derivative over here and just convert it back to what I started, right? Except I have this arbitrary constant there. So that's the idea, okay? I'm still going to treat x as a constant, right? And be dealing with y as my variable in that instance. Um, I could also, take something like this and evaluate a definite integral, right? By treating, again, in this case, x is a constant because once I find my antiderivative, I'm just going to take this expression and I'm going to replace y with the 2 since I'm integrating with respect to y. And again, I just keep x as a constant. Notice my constant of our integration cancels out of the problem here after I distribute the negative through. I'm not going to go through all the arithmetic there, but it's just a substitution simplify. And therefore, I'm left with an expression in x. All right, so where that comes into now is essentially if I start with these double integrals here, okay, I'm going to start on the inside, evaluate this integral. Once I get a quote unquote solution for it, then I'm going to plug it in and then I am going to evaluate the integral with respect to y. Um, I'll explain why this works this way, but notice for this definite integral, and if you can evaluate these on Desmos, okay? Sometimes yes, and sometimes no. It's a pretty simple process. As a matter of fact, if I maybe do this one for you here, let me get Desmos up here and all right, just to show you this. This is probably going to be a long video. I apologize for that. But if I want to evaluate definite integrals here, I'm going to scroll down here to I get the integral sign, and then I'm going to come up. I mean, you could type this in any way, but this is what I find to be a little bit easier to deal with here. And then what do we have? X squared y plus 3y. Okay, so x squared y plus 3y. Okay. And I'll close my parenthesis there. And then I got to get the inside going from 0 to 3 and 1 to 6. Okay. So I go 0 and 3 and 1 and 6. So when you, whoops, wrong number. One more time. Oh, and then I have to go. Let's see, forgot my dx dy, right? So I'll go dx dy. And once I type that in, you can see that the number just pops up over here. Okay. So pretty simple, it's just a matter of getting it keyed in there. And like I said, for simple ones like this, it does evaluate it. Notice if I integrated with respect to y first, I have to also put the 1 to 6 on the inside and the 0 to 3 on the outside. Okay. So again, just be careful the way you key these in. Sometimes it matters in the order in which you do these, dx, dy, but generally speaking, we start on the inside first, okay, if we're going to do them by paper and pencil technique. So let me pull an example of that in here for you, okay? So this is the problem that I'm working with here. I'll leave that over here, but we don't need to see this over here. So what I'm going to do, or what you saw that I did here, was I just took this bit right here in the middle and I pull it off to the side. Okay, so I'm going 0 to 3 and my dx, everything in between. And like we said, just in that other example, since I'm integrating with respect to x, I'm going to treat y as a constant. So I just take this term, x to the third over 3, and treating that as a constant, 3yx, right? Okay. And then I just replace, again, the x's with 3. And I just put 0 here because we're going to get 0. I didn't show the substitution, but I think it's pretty obvious we're going to get 0 in this expression when we replace the x with 0. Okay, so I end up with 18y. What I'm saying is this is equivalent to 18y. So I'm going to replace this now with 18y. I put the 18y in there to find the antiderivative, evaluate it using the fundamental theorem, and I get my 315. Okay, so I think you would all agree that, you know, Desmos is a lot easier just to type that in, but you know, obviously we can do that. There are problems of that type with the fundamental theorem of calculus. Okay, so I'm going to get rid of this, and let's move on to our next example. All right, so we got a couple of these here. I'm going to show you, you know, like I said, I don't have time. This is going to be a long video to begin with, but anyway, all right, so sometimes they're going to give you problems like this, and they'll give you the limits of x and y, and they may give you a suggestion here, dx, dy, or dy, dx. And again, where that's coming from back here is just, you know, what we started with as a simple integral and an example where they gave you the problem. Now they're just telling you over a region, but this is a rectangular region on the xy plane. X is going from 4 to 5 and y is going from 0 to 5. Okay, so you know, I have this little phrase up here. Sometimes it's you know, you can evaluate it one way or the other, but sometimes one way is better than the other. Okay, so meaning x or y first. So for this particular one, notice the very first thing you do, if you key it in there, you're not going to get the exact answer, and you're going to have to type one in. Okay, so you're not going to get away with using Desmos all the time. We can sometimes, but not all the time. So, you know, how do we get this big mess right here? Well, let's take a look at how to do that. And I am going to just pull this up first before I explain to you why I chose the method that I did. Okay, but you can see that's the same problem here. Okay, and notice I put the y on the inside. Now, no pun intended, but why did I do that? Oh, math is so fun, right? Okay, well, think about it. You're going to use the chain rule here, right? And since I have a composition of functions up here, notice if I take the derivative of either x or y, if I take, and I got this y I got to account for my substitution, it makes sense to me, okay, and hopefully to you, that, you know, when I take the derivative of this numerator with respect to, or this exponent with respect to y, I'm going to get 2y, or a form of y out there, okay? So I'm going to use substitution here on this integral, okay? And I'm going to do what I normally do. That's my composition of functions. So I let u be x plus y squared. I take the derivative of u with respect to y. Remember, we treat x as just a constant. It's you know, look at that as the partial, and we get 2y. And now I need to be accountable for, when I make that substitution, and it looks pretty clean here, I'm just replacing the x plus y squared with u. And I come over here and solve for y dy. So I just need to divide both sides by 2 and multiply by dy. That means I got this right here in terms of du. So I'm going to replace that with du. All right. So over 2. So I put my u here, right? Place that. My du over 2, I'm just going to write as 1/2 du. It's the same thing as du over 2. And now I got to make the changes over here for my limits of integration. So do what I normally do, right? I'm going to start off with, since I made the substitution here, I'm dealing with an integration or an integral with respect to y. I'm going to replace in this expression y with 0. Okay, so when y is equal to 0, u is just going to be equal to x, right? So I just write that down here. So when I let y equal 0, u is going to be equal to x. Now, when y is equal to 5, now I'm going to get 5 squared, or 25, so it's going to be equal to x plus 25. That kind of went off on my scan here, so I apologize for that, but you'll see I make the substitution down here, okay? So when I do that now, I have u equals, or my limits of integration go from x to x plus 25. Now, again, you may need to stop this video or scroll back just to hear that again. But all I did was make the substitutions as I normally do. Very nice integral to evaluate, right? E to the u is just e to the u. I evaluated at x plus 25, subtract from it, evaluated at x, and now I got this thing, all right? So all I'm going to do now is take this inside integral right here, and I'm going to replace it with this expression here. So I just put the 1/2 out front, and that's what I'm going to find the antiderivative of, okay? Well, this is pretty easy, right? Because the derivative of e to the x plus 25, since that composition is just, derivative of the numerator is just 1. I don't need to use substitution there. The antiderivative is just going to be e to the x plus 25, and the antiderivative of e to the x is e to the x. So all I need to do is evaluate both of those expressions at 5 and 4, okay? So that's all I did. I replaced the x with a 5, okay? Right here, replace with a 5, that's going here. Replace the x with a 4, that's what's going here. Okay, that's 29. All right. And I make that subtraction when I evaluate it, right? Because I'm going to subtract it, evaluate it at 4. I distribute that through, and I'm just going to leave it as such. And there we go. Okay, so that ends up being the same thing. So we couldn't do that on Desmos. We had to use the method of substitution. We kind of had the option also here to decide, what do we want on the inside? Now they kind of, I don't know, maybe if you look at that, maybe misleading you there. Notice I chose to move the dy on the inside, right, first, okay, and go with 0 to 5 on the inside, for y. So, they had dx here, so I don't know if you look at that as them tricking you, but anyway, or trying to lead you down astray. But it was, again, very easy to use substitution if I integrated with respect to y first, just due to the nature of what this integrand was. Okay, so there's another example. Now, you've got a lot of each of these types to do, and I can't, like I said, this video is going to be long enough as it is, but I want to move on to what they represent here, okay? And this should kind of make sense to you, right, before, because when we were dealing with integrals, we were talking about area and rectangles. So now we introduce the third dimension, or the third axis, if you will, the z-axis. And so now we don't have rectangles we're going to be adding up. We have a rectangular cylinders or square cylinders that we're going to be adding up, okay? And depending on the nature of these, so we'll just call them rectangle, because not necessarily they'll be the same width and length and so forth. But either way, and how many subdivisions we have here. But we're not going to get into all the theory of the definition. That's not what we want to do. I just want you to understand that instead of adding up areas of rectangles, we're adding up volumes of rectangular prisms, okay? And infinitely many of those will give you the exact volume. So what are we doing here? Well, it wants us to find the volume under a given surface and above the rectangles with the given boundary. Now, what we mean by above the rectangle means is that if we graph in the plane, the XY plane, X goes from 0 to 1 and Y goes from 0 to 3, we're just dealing with that to be, let's just say that's like the floor of a structure. Now I'm going to graph this in a live version of this, but I'm just trying to show you that, kind of where we're getting this solid or what we're finding the volume of. So what I did here, the function, this Z is actually going to be kind of like the roof. So the X and the Y's are going to be more or less the walls, okay? And the walls are standing on that rectangular floor, right? It's a 3x1 floor, so to speak, okay, whatever units we're dealing with here. And notice, in this one here, it's a relatively simple example. And notice we can, integrate in either order. We're going to get 20 for our volume, okay? So, and I'm not going to go through and actually, do the actual integration by hand here. We could do it on Desmos, why not? Okay. But what I did want to show you was that if I get into this particular one here, if I find, yeah, there it is. Just so you could see, here's my x-axis. Now, when I graph x equals 0 and x equal 1, it's really just a vertical plane, right? That's going up and down here. And so if you look here, kind of look down that hallway here, we've also got a wall here going from y equals 0 to y equals 3, okay? So there's my y-axis here. So I'll start spinning this around a little bit. So it's kind of like we're looking, if I can get it to stop here, this, I don't know why when I'm in, try that again, I don't know why when I get into Zoom, this thing doesn't like to cooperate all that much, but let me try to be a little more careful here. Of course, I went too far. We're looking down that, it's kind of like that parabolic roof, so to speak, okay? But there's still a wall there that we're looking through, but that roof kind of sags in, okay? So we, probably that might be the best angle actually, just looking where it came up. But there's the floor, right? Okay. Like that would be like looking up from the basement, okay, into the floor. Now that's looking down. Okay, so that gray part's my floor. And then I've got these four walls here. Maybe if I look down on top of it here, if I get the Z-axis right out, okay, we can get the idea there. That's that rectangular region there. And again, that roof is going to be that parabola. Okay. So I don't know, just kind of, a nifty way of looking at that. That parabola is going to come up here and be that roof. Okay. So that's the volume that we're finding. Okay. And evaluating the definite integral. Okay. That's the roof. Those are our bounds of our base here, which is again a rectangle. And that's important to note here because we're going to get into ones that are a little more complex to that in this next example. But that's how you evaluate those. Okay. We're going to skip that one again. And now we're going to talk about integrals over different types of regions. So again, the last example, we had a base on the floor in the XY plane that was now formed by a rectangle. Now what we're dealing with is some irregular object. So order here is going to matter, and we have to take a look and see and make sure what we have as our functions, all right? So for this particular one right here, we're dealing with a function, right? If we run a vertical line test, this blue line is a function, and so is the red. But if I went in this direction, right, that blue curve or graph there, and the red one, both wouldn't pass the vertical line test. So I got to be dealing with functions here. So I got to go up and down here. Okay, when I make up my regions that I start adding up. So when I do that, that's going to be my inner function, okay? And I'm going to say that y is going to start from g of x, right, on the bottom and go up to h of x, okay? That's going to determine that region that we're going or that we're integrating over, okay? We're going to start at g of x, we're going to end at h of x. All right. Then when I consider the integral of x, well, x is going to go from a to b, and that goes on the inside. So it's kind of like I'm going to find the integral with respect to y first, okay, because that's where my functions are. And if you look at that, I'm replacing these with functions as my upper and lower limits. So when I find the antiderivative, I'm going to put in an expression of x. Then when I evaluate the outside integral, I'm going to have everything in terms of x. Okay. Over here, notice that's not a function, or h, this one wouldn't be a function. I guess that one could be, but it's kind of looks vertical there. But this one's very obvious, wouldn't pass the vertical line test. But if I look at it as the independent variable as y, both of them do pass that vertical line test. If I flip that axis over and this was the independent variable. Now, again, that's what I'm just dealing with x and y. So I want my integral now, my x, to start at g of y, like we do here, and go up to h of y. Okay, so I'm going to start here, x will start here, and go up to here. Then y is going to go from start at c and then go up to d. That's what would be my outer integral. Okay. So again, once if I evaluate the integral, notice when I find the antiderivative of the multivariate function, I'm just going to treat y as a constant, and I'm going to replace all the values of x that I find the antiderivative of with expressions in terms of y, and then everything's going to be in terms of y, and then I'll evaluate the integral from the new numbers that are given, in this case, c to d. Now that sounds probably a lot to listen to, and I'm just trying to, give you a sense of, what we're trying to do here before we actually go ahead and illustrate it. So here's a particular one right here, okay? So I've got to decide now, where my functions are, and it's pretty obvious with this direction here. I've got a function, right, in terms y in terms of x and y in terms of x squared. So if I looked at that, then I'm going to evaluate my inside antiderivative with respect to y first, and y is going to start at x squared, and it's going to go all the way up to 2x. So there's and this is just a Desmos right here expression, okay? And well, it's set up here actually. So, again, I got this region. This is the region. This would be my floor. My roof is going to be this thing. I'll get into this live diagram here in a second, which is just x plus 2y. That'll be the roof. And so again, I take a look at my functions on the inside. Y is going to go from x squared up to 2x. That goes on the inside. I just take the expression for the function that's given, which in this case is x plus 2y. And then I take a look at, okay, well, what's x going to run from? Well, x is going to start at 0 and it's going to go over to 2. Okay, and that'll cover, I guess, what I want to say, that area region of the floor. And then the roof is just going to be the integrand. Okay, so that's how you set those up. What I'm going to do is I'm going to try to get into this. I think I should already have it. I'm trying to save as much time. This was x plus 2y. That's not the one I want. Here it is. Okay. So x plus 2y. So the roof is this light blue. Okay. This light blue. And this was an older picture, so don't try to match the colors here. Okay. But it's the light blue plane. Okay. Which is that slanted plane right there. Okay. Then the floor, if I kind of get the z-axis out again, is going to be that dark blue. That's the line y equal 2x, right? Okay. And then the other one kind of disappears, but I'll try to tilt it just a little bit so we can see it. Maybe. There it is. The parabola, right, that's on there, it just seems to want to disappear here. But y equals x squared. If I'm trying to get the z-axis out so that you can see that the blue one is the line y equal 2x, and the red one is the parabola y equals x squared. So if we're looking straight down on it, it appears to be the parabola and the line just drawn on a plane. But those things are protruded up. That's what these equations or surfaces are doing here. When we plot them in 3 dimensions relative to variable z, because it's just going to be like one parabola stocked on top of another, on top of another, on top of another, and the same thing with 2x. Just keep stacking these lines up, and that's what's building your walls. And then the roof is going to be this x plus 2y. Okay? So again, when I set that up, like I said before, the y is going from x squared up to 2x. That's my function, and the x is going from 0 to 2y, and there's my roof, and I'm just going to evaluate that thing on Desmos and move on to the next problem. Okay, so I got one more here to show you, and that is, I believe, number 7 here. Okay, and so it just says evaluate this double integral. Okay, so they give you something here again to do in terms of, again, it's really already set up for you. And notice how they have the function in y for the upper and lower limits here. So I just wanted to show you here one with the, that give you an additional example. So let me go ahead and do that. If I can. Okay, so let's see if I get that over there. That's the one I did earlier. I'm gonna get rid of that, and I want to pull this one over. I got 2 screens here. Okay. So again, I just take this thing out here, right? I pull that over, and all I need to do is just take my inside function here, which goes from 3y to 6y. That's a 2 over x. So that's going to be 2 times the natural log of x, evaluated at 6y to 3y. Simplify that expression. Here's where that logs come into play, right? If we take the difference of a log, right? That's the log of the quotient. Notice that cancels out here and just leaves me with the natural log of 2, all right? That's just a number. I come over here, now I find the antiderivative. This is just a 1, which is going to be y, and that goes from 8 to 9, or evaluated 9 minus 8. And so I'll just simplify here. 9 minus 1 is 8. Okay, and I have the, or 9 minus 8 is 1. I don't know where that 1 came from. Must have had a little brain freeze there, but that's 9 minus 8, excuse me, which is 1. So I'm just left with 2 times the natural log of 2. Okay. For this example I just showed you, I could have also flipped it around and done it the other way. And I'm not going to go through all that, but like I said, it's just I'm treating x as a constant over here, integrating with respect to y. And notice I end up here with a expression 2x. And then now I'm just going to go ahead and substitute that in here, and I take the natural log, or 2 times the natural log of x, evaluated at 6y to 3y. Notice I end up with a similar expression of what I did earlier, and I get 2 times this. Again, the difference of a log, 2 logs, right? The same base is just going to be the quotient of, or the log of the quotient of the 2 things. And again, that simplifies to just 2 times the natural log of 2. All right. I don't think I did that one. No, I did not. Okay, so anyway, there's that one for number 7. Oh, this is the one I wanted to take a look at. Yeah, this was the last graph. Okay, so the last one here, number 8. Notice again, I have this parabola, x squared and 2x. And I did want to show you that, if I take that region bounded just by those two values here. Notice again, there's no X and Y limit here. It is possible, right, to look at a function of X and a function of Y. And that's what I wanted to, I guess I wanted to show you this one here. So if I would go in the inside and let's just say, for this one here, I want to start and see what Y goes from. Y is going to start at X squared and go up to 2X. Okay, and here's my roof, so to speak, that goes in the integral here. And then on the outside, X is going to go from 0 up to 2. Okay, notice again, if I just evaluate that integral on Desmos here, all right, I get 512 over 35. Now, if I did look at this, notice if I turn it the other way and take a look at X as a function of Y, notice they would still pass, right, the vertical line test, both the red and the blue, or red and the black. So now if I set it up, so X is on the inside, and I solve this equation over here for X, X would be Y over 2. So this would be the line X equals Y over 2, right? That's the same equation. I'm just solving for X now. So I'm going to go from Y over 2 here. And if I solve for X over here, I'm just going to go ahead and take the square root. And since I'm in the positive part of the Y-axis, that's just going to be the square root of Y, right? X will be equal to the square root of Y. And so I could still take that same roof and go from, again, X over 2 up to the square root of Y going in this direction, and then say, okay, well, Y goes from all the way from 0 up to 4. And notice those two numbers are going to be the same. So, it is possible to look at that either way. I would probably just do this because they're expressing Y as a function of X. So that tells me I'm going this direction, and put Y on the inside. I guess if they give you Y as a function of, put Y on the inside first and just use the diagram like so. Okay. Again, just to show you what looks like, this one's pretty complex in terms of the graph, but that would be like the floor plan, so to speak. Okay. And then this is going to be your roof, which is this really crazy purple thing here. Okay. But you can see that, that parabola, if I get there, like I said, that parabola just wants the distance. If I just turn it a little bit, there it is. You can see, okay, that's that little region right there. And then we got a purple roof inside there somewhere. And that just kind of gets a little crazy here with the, even with the 3D software, it's pretty tough to visualize. But I think you can see like kind of back here just a little bit. Okay. Let me go around this way here, maybe. Okay, we're kind of looking down in there now. Okay, that area. I know I got these axes all crazy here, but like right in there. Okay, and then we got this kind of slanted purple roof in there. So we do have a three-dimensional object. And remember, the floor plan's just that. I just got this. This is the positive direction for my y-axis, so it's kind of backwards, but nonetheless, hopefully you're getting a feel for what that looks like. I tried to orient it the best I could here with this one here. I have a still shot, I believe, over here. Oh, no, I don't. I thought I did. Okay, never mind. All right. So getting kind of long here, but hopefully what I did was, again, give you an idea of how to set these up. And it is hard. You're going to want to probably play back this video and scroll back into different parts to make sure you get it. But I hope this helps. The problem with these online classes, or I shouldn't say the problem, but the biggest challenge is just the time factor. And really, this is a lot of material to cover in such a short time. I feel like I'm even rushing myself to keep the videos to a reasonable length, but yet, you're getting hammered here, as far as the amount of topics and how quick things are coming at you. So anyway, hope the video helps here, and as always, let me know if you have any questions. And if you've looked at all these videos in order, then this is the last one, and so that would be it as far as the course is concerned, and that would be I guess time for farewell and God bless. I wish you well, and this has been a joy for me.